Hi guys, can I get a shout out? Sound check.
Hey, how's it going, Professor?
Good,
Yeah.
thanks. I see. What happened?
Just testing.
Testing. Okay, guys. So let's see. Content screen. Let's see. Okay. Anybody have any questions about the like overall concept of small signal versus large signal before we get started? No. Everybody clear? Arthur, you've shown up on my screen, so I'm gonna have to ask you. How are you feeling about small signal? Arthur?
Yeah.
Yeah. So how are you doing with small signal concept? Are you getting it, or is it like just don't know what?
I was doing the homework before this class,
And does
so I
it?
can't really say about the small signals.
Yeah. So you didn't hit any of the small signal. I assume there's some small signal questions in there. Did you hit any of those? Any of your problems? Small signal problems?
So far, no. I think I'm halfway there.
Okay. Okay. So okay. Well, we'll see how hopefully it'll homework will help you guys. Yeah, the reason I keep bringing it up is because it was a concept that was very confusing to me. So I don't think I ever really even got it in undergrad until I started working later. And so okay, so let's and we're going to well, I'll do a few examples in small signal, and maybe that'll help. Okay, so. Let's see. Again, I think the concept of small signal is, we have these different models of how, oh my God. It's like clockwork, guys. Sorry, I have to issue it. I thought I would have done this before. I'm sorry, guys. I have to go close the drapes again. I'll be right back. Here, guys, this is put a face to this miscreant here. Anyhow, hopefully she'll be quiet now that I close the drapes. Sorry about that. All right. Okay, so again, this concept of small signal comes from the idea of doing hierarchical design. Okay, so hopefully this won't confuse you, but this is a concept that you'll have to understand no matter what type of engineering you guys do. So, if you're talking about, device physics at the level of, NPN devices, if you're looking at it like that, there's a complicated equation for current density here. It has to do with doping concentrations, charge of an electron, width of the gate, width of the base, a bunch of stuff. I mean, I'm like, whatever. So it's electric fields, charge, those kind of things. Okay, so if you try to design circuits, any kind of circuit at this level, you wouldn't get very far. So we have the next level of abstraction at the level of, okay, let's just, both from a symbol standpoint and from a model standpoint. So I said, okay, we have this, let's call this thing, the circuit element, okay? And that circuit element, again, as a model of abstraction, it has, if it's biased a certain way, so in forward active, we can make it like a simpler level of abstraction. So this is I'm just going to call it I sub c over beta, and I sub e is I sub c plus I sub b. Okay, so this is basically like we've restricted the range of operation of this device to come up with this model, which has current sources, diodes, basically a little bit simpler to deal with. And then doing small signal analysis is like the next level of abstraction. So now we're saying we're even gonna restrict the operations even more. So we're gonna bias at a particular I sub c or VBE. So for us at the moment, that's kind of practically the same. So when we say we've got it biased at a particular point, then we can further simplify this by having, so instead of having an exponential curve for I sub c, we can just say the change in I sub c, if we're biased at around like a point, a specific point I sub c, then if there's a small change around that, just for the small change, we can use this concept of transconductance times the V, okay? And instead of the input diode, we can have like a resistor. So this we call R sub pi. We call this voltage. It's just the expression V sub pi. So I'm gonna change this. It should be V sub pi, and then GM is equal to I sub c over V sub t, and R sub pi is equal to beta over G sub m. Okay, so we're basically, restricting these, we're sort of trying to simplify the models here. And by the time we get to the small signal model, so this is the small signal. Oh, by the time we get to the small signal, we're just multiplying. So, we've got, resistor values, and we have we're just multiplying voltage by this value. We don't have exponentials and stuff like that anymore. And sort of the step from here to here is we are just going to operate the device so that we're in this forward active mode where I sub c is exponentially dependent on VBE. So this corresponds to this level of simplification. Okay, and then when we go from here to here, we're going to say, okay, we're only going to work over, so we're going to be in the same forward active range. So it means we'll get an exponential relationship between VBE and I sub c. And furthermore, we're going to limit our activities just to the bias point. We're going to call it a bias point. That's the central location where we're only going to be moving around this slightly. So, sorry, I put in I sub c here. It should be VBE1. So this will be a point, and it'll give us a central value for IC1. And in this really small range of operation, just here, the change in I sub c is GM times change of VBE. Okay, where GM is dependent on IC1 over V sub t. Okay, so we're saying we're going to just operate in this really small range, and then we don't have exponentials, etc. Now, you could say, well, okay, you've really made your life simpler by limiting the operation, but then is this useful? And the answer is yes, because a lot of times, the way these amplifiers work is we have very small changes. We usually are dealing with small signal levels. And so the idea is really powerful because of that. So we can limit it, the range, etc. Arthur asked, does it require 2 VEs for the bias point? Can you ask that, Arthur? Can you be more specific?
Yeah, I think I'm just kind of confused about why you only have like 1 point for VBE1 instead of 2.
Oh, like the either end of it?
Yes.
Yeah. So the way they look at it, a lot of analog design, the signal is positive, and in a lot of analog signal, you have, you have a bias point, and then you have a positive and negative going signal around that bias point. So instead of having a high signal and a low signal, the way they define it is this sort of what's called a common mode level. And then they define sort of a delta signal around that. That could go positive or negative by the same amount. You could think of it as a convention. It's like easier on the math. You can do stuff like, the sine waves, etc. You can deal with them a little bit easier because positive going, negative going is the same. It's just a convention. They've sort of picked the mid-level and called that a single bias point, and there's small excursion around that. But effectively it gives you two ends. The thing is also these two ends it's a little bit of a fuzzy, like the bias point is not a fuzzy concept. Like if you're, as you'll see in chapter 5, you'll be actually building a circuit. It's usually a resistive circuit or something like that to define a single bias point. and then you'll add a signal. The input signal will be around that bias point, if that makes sense. So from a circuit standpoint, you'll see that it's easier to just make one bias point, and then your input just gets superimposed on that bias point. And then the ranges of that input can go higher or lower a bit without having to define it too tightly. I hope that helps. Any other questions, guys? So that was sort of like the small signal. So now let's do an example, okay? So, I mean, you guys have access to this, but just try to do it. So what is, let's see, let me see what the question is. So let's say we start with, so this is actually an example of maybe going to what Arthur was saying about seeing how you only have a single bias point and then you have movements around it. So basically the problem is this. It is example 4.10 in the book. Okay, but the upshot is that we have a bipolar transistor. We're just for this example, we're hooking up the collector directly to a supply. And that's 1.8 volts. And then we have a bias voltage, which is, so whenever you see this symbol, guys, it's a battery. So this is a battery. And usually this is used to show constant voltage source. And usually when you see like this symbol, usually it's meant to specify a changing signal, usually voltage. Okay, so you have this voltage that in this case is supposed to be signal from a microphone. So somehow we've got a bias voltage of 800 millivolts. Sorry, I shouldn't say VBE. So we just, let's say we call this 800 millivolts. Because VBE is the 800 millivolts plus whatever is this signal value. And VCC is 1.8 volts. Okay, and then this guy's called Q1. They're also giving us I sub s as 3 times 10 to the minus 16 amps. And they are telling us beta is equal to 100. And they're telling us that Q1 is in active mode. So I guess that's a clue that they're not asking us to double check to make sure it's in active mode. They're telling us that it's in active mode, but you can see it, right? It says 800 millivolts from base to emitter here. And we got 1 volt from here, the collector to the base. So the collector base is reverse biased. The base emitter is forward biased. Okay. So now they gave us the model for what this looks like in small signal. So now this is a point, another sort of confusing thing about small signal. In small signal, we're only looking at things that change. So voltage sources, current sources, we are only looking at changing things, okay? Changing things. Now, there's, like I said, this VCC is constant. It's not changing. So it's just gonna look like ground because there's no change there. So in small signal, batteries or constant voltage sources look like a short. In other words, you know, closed switch. Okay. And then also in small signal, current sources that are constant look like opens. Okay, so be really careful about this because, you know, this is one of the places where a lot of people go wrong when they're going from a large signal to a small signal schematic. Okay, so when you have a constant voltage source, it just looks like a short through it because there's no change in this device, and small signal is only the changing components of whatever you're looking at. Okay, so then this G sub M. Okay, so again here, this guy is shorted across, and we just see this changing V1. So I'm just going to draw the V1. And then the emitter is grounded. Okay, so, you know, why also, you know, why can we get away with, I mean, we're just only looking at the changing elements in the small signal. So we've already used the 800 millivolts, as you'll see in figuring out this problem. We'll always already be using the 800 millivolts to calculate the I sub C current for the G sub M. So we don't need that anymore. Once that's done, it's constant, we're good to go. Same with VCC, we're just using it to make sure this guy's in forward active. So we've already used it by the time we get to small signal, and we don't need it in this small signal value. Okay, so this is the problem, and you guys try to give it a shot at solving it. So basically what it's asking for is figure out G sub M and R sub pi. Okay, so if V1 is equal to 0. So if we don't have any signal modulation there, try to figure out these two values. Once you guys take a little bit of time trying to figure that out, and I'll ask one of you guys to help me out solve it after a few minutes. Thanks. Okay, guys, let's try to solve it. So I'm gonna start calling people out. Haha. Joanna. Joanna, are you there?
Yes.
Could you help me try to solve this?
No.
No? Come on, let's do it.
Sorry.
Let's do it together. Okay. So any idea where to start?
Can we say that v pi is 0 first off?
What's that?
Can we say that v pi is 0?
V pi is boy, that's a good one, Melvin. Yeah, I guess you could say V pi is 0. Yes? Mm-hmm. Yeah. Now, like we're looking for GM and R sub pi. All right, so the first thing, so John, remember the equations for GM and R sub pi? We have it here. You with me?
Yes.
Okay, so let's write those down first. So the GM is I sub C over VT, and R sub pi is beta over GM. I hope I got that right. Okay, so so what's given, or what do we know, and what's not given here? Let's just look at the GM one right first, right? So do we know what V sub T is?
Is that 26?
Yep, 26 millivolts, yep. So V sub T is 26 millivolts, so that's given, or known, let's say. Not given, no. I guess it's God-given, known. Okay, so what we need to do is figure out I sub C, right? Because we don't have they just told us these voltages, and they just told us these voltages, and they told us that Q1 is in active mode. So we have to figure out what I sub C is, okay? So step one is figure out I sub C. Okay, do you remember the equation for I sub C in forward active mode?
Is it I sub S exponential VBE over VT?
Mm-hmm. Yep. Okay. So what would this be here in this problem? Jump in, Joanna. Joanna?
Yeah.
You're not having fun with this, are you?
No, I'm not. I don't like being put on the spot. I'm sorry.
Okay, I'll let you go then if you're not having.
Sorry.
Okay, so let's try, since Melvin spoke up first. Melvin?
Yep. So I'm thinking that we just say is VBE 0 because it's the base emitter difference?
I'm glad you said that, although it's not correct, but it's an important thing. So this VBE is now this is the bias point for the small signal analysis. So this would be, we're trying to calculate this value. Okay, so this isn't the small signal VBE that we have in this equation. This is all the whole VBE. So it would be this guy. So it would be the 800, because what you're doing is you're saying, okay, I'm going to figure out my I sub C on my bias point. And once I have that value, I've got this GM thing that's just a small variation across it. So when you figure out, when you're doing the I sub C calculation, you'll have to use the VBE, the large signal VBE, which is basically everything. So in this case, it would be actually this value. Okay, so,
and this is set by the manufacturer, so we just know that.
No, actually, this is your design now. So
okay,
let me put it this way. So okay, this is the manufacturer sells you this guy. Typically, it sells you a bipolar transistor. Okay, so you got this bipolar transistor. It'll have a certain beta, so that's manufacturer created that. And it'll have a certain I sub S. In this case, it's 3 × 10⁻16 amps. And I'll have a few, there's be a bunch of other things, but we're not getting there yet. But those are the main things that you'll get from the manufacturer. Now it's up to you to hook this up in your circuit in some way that it does what you want it to do. Okay, so it was up to you then to put this guy at ground, to put in this case, this was a microphone. So put your microphone between the base and some voltage source that would, I should keep saying 800 millivolts. To make this forward bias, and it was up to you to put some kind of a voltage source to make this collector base reverse bias. So the manufacturer is just selling you the device typically, okay? Then you hook it up to get it to do what you want it to do. So you were the guy, and again, like we'll see in chapter 5, how to design the circuit that biases this up in a certain way. But the designer basically creates the bias point for the circuit. It's a design choice. Okay. Does that answer the question?
Yeah, that makes sense, because when we're doing a small signal, we know that the input signal is 0. So originally it was 800 millivolts. So I was a little bit confused.
Yeah. Now I'm glad you said that, because it's a key point, the difference between small signal and large signal model. So this I sub C that we have in the G sub M, this I sub C is this I sub C here, and this is our bias point. So we need to calculate this bias point using our large signal value. And then all the small signal stuff happens around that. So G sub M, R sub pi, they're all only meaningful around some I sub C that's dependent on your large signal VBE. So basically this ends up being I sub C is 3 × 10⁻16 amp exponential of 800 millivolts over 26 millivolts. And that, I have it in my notes here somewhere, it is 6.92 milliamps. Okay. Cool. Okay. So now, Melvin, what do we do with this? So now we got to go back and do G sub M and R sub pi, right?
Yeah, exactly.
So what do we do with it? So G sub M is.
So now we have G sub N, and we are looking for R pi, and we know R pi is dependent on G sub M.
Yeah.
And we just plug those in.
Yeah, we don't have G sub M yet. I mean, we're almost there, but we have I sub C.
Oh, okay. Yeah.
Yeah.
So I sub C divided by the given 26 millivolts.
Exactly. And that ended up being, so,
0.266 Siemens.
yep, 20, sorry, what did you say it was?
0.266 Siemens.
Yep, millisiemens is what I have, same thing. Or you could look at it as being 1 over 3.75 ohms, same thing. Okay. Okay, now we know what's about our supply.
I'm crunching the numbers right now. 1 second. Is it just a 375, I think?
Yep, that's it. So it's just beta.
Yeah, same answer.
Yeah.
All right, nice.
Each of them is 100 over 1 over 3.75 ohms is 375 ohms. Okay, so now a couple of things to notice here. One of them is that notice that if we wanted, so this G sub m, remember this G sub m is, so change in output current is G sub m times change in input voltage. Just in this small region, okay? And so, you know, to get a high gain, remember this is the output current that goes, you know, we put that across a resistor to get gain. So, you know, to get a high gain, we want a big change in output current with a small change in input voltage. That's like that would be a good thing, right? Because we want a high gain, we want that slope to be high between a small change in the input to a large change in the output. So we would typically, for reasons of high gain, low, and a whole host of other reasons, we want to make G sub m as high as possible. And you can look at G sub m here. Notice we really only have one thing to play with in a bipolar transistor for G sub m. We can just increase I sub C. And the way we would do that in the circuit, okay, I sub C is dependent on this value, right? If you wanted to increase I sub C, it's basically, again, the manufacturer gave us I sub S. We don't have any control over that. V sub T is just as a constant. So we can increase, as designers, we can increase V sub BE. Like if I made this, remember every 60 millivolts change on the input, base emitter input, gives a 10-fold increase in I sub C. So if I made this, change this from 800 to 860 millivolts, then I sub C would go from 6.92 milliamps to 69.2 milliamps. And my G sub M would go to, you know, would be 10 times bigger, okay? So basically that's my degree of freedom, is increase I sub C or decrease it, depending on which way I want G sub M to go. And usually in this configuration, your knob to tweak as a designer is the base emitter voltage, okay? And the reason why you can't just keep cranking up I sub C, like we talked about last time, is power consumption, because you're almost always, I shouldn't even say almost, you're always under power consumption restrictions, because this power consumption is bad. It's, you know, you have to remove the heat of the device. The device actually heat up, like your computer heats up, your cell phone heats up, and, you know, especially battery operated devices, they'll discharge more quickly the more power your circuits use, okay? So that's one thing to think about, okay, G sub M. And then R sub pi, this will be important in chapter 5, but notice the R sub pi is ends up being a relatively large number in this configuration. meaning that this small signal input resistance into this device ends up being a high value. And we'll see why that's actually usually is a very good thing. So, and you can increase that by a bunch of different ways, but we'll see how that works. Okay, so those are two things to think about. Okay, so thanks everybody so now I'm gonna give you guys now the next example. So I'm gonna pick on a bunch of other people. So thanks guys for jumping.
Sir, I have a question.
Yeah, go ahead, Kevin.
Thank you. So if V1 was 20 millivolts, for our calculation on IC, would we have VBE as 820 millivolts?
Oh, did I put an 820 somewhere?
No, I'm just saying that you gave us if V1 is equal to 0.
Yeah,
If V1 was equal to 20 millivolts, when we're calculating IC, would VBE be 820 millivolts? Since you increased the...
Yeah, it would be. I guess you could say it would be. Yeah.
And that's basically when we speak into the microphone, we're giving that small signal, we're adding it up to that voltage, or?
Yeah, what you typically do is your input signal ends up being, and so, okay, this is a good question. What's a small value? A small value is something that's smaller than, like significantly smaller than V sub t. Okay, so if you're at 20 millivolts input, that may be small signal. It might be changing your large signal value. But like a more appropriate value for a small signal input would be maybe 5 to 10 millivolts change. And in which case you're not going to see a big change in your I6C over that range. That makes sense. So you would just, in that case, you would just pick the V bias of 800 millivolts and just deal with your 10 millivolts as a small signal on top of it, or your 5 millivolts. Yeah, by the time you get to 20 millivolts, again, what you want to see is the threshold of, what is small signal. Your V1 or input voltage, you have to compare it to V sub t. You don't even compare it to VBE. You have to compare it to, so you want V1 to be much smaller than V sub t. And V sub t, again, at room temperature is 26 millivolts. Okay, so I hope that helps. And it's kind of a little bit fuzzy, like, hey, is like, is 15 millivolts okay? Well, yeah, maybe okay, maybe not okay. And the reason it's fuzzy is because what that'll do as your that's input signal increases, it's doing something else to your amplifier that we're not going to cover in this class, and it's called distortion. So, again, those are you guys who are into like maybe audio, if your signal is too strong into your mic, it tends to sort of make your recording or your amplification non-linear. So you have to, sort of like the mic itself is tuning itself to like adjust for your volume to a certain extent. Professional mics don't do that, I guess. You actually set it. So if your input signal gets large enough, what it'll do is it'll start screwing around with the bias point of this amplifier, and it'll cause some nonlinearities. So you can't just have your input signal be just anything. It has to be really fairly small. And the bigger it gets, it's not that the small signal model falls off of a cliff all of a sudden. It just gets less and less of a good approximation to a good design, if you see what I'm saying. So notice that this is really all these levels of abstraction. This is all really the same device. It's just one device you bought from the manufacturer, right? But you're trying to model its behavior under different operating points to make life easier for you. And if this input signal changes too much, then your design isn't going to do what you thought it was going to do. It's going to have distortion. It's going to have other issues that, again, we're not going to get into in this class. So I hope that was a very long-winded answer, Kevin, but hope it kind of gets to what you're asking. Okay, guys, so let's go to a follow-on from, oh no, wait, did we finish this? Okay, that's cool. Okay, so we have, this was the A of this sample. Oops. So question B from the same example is, if V1 is 1 millivolt, how much will I sub C and I sub B change? Okay, I want you guys think about that for a minute, and I'll see if I can trouble someone else. Okay, guys, let's take a shot at this. Robert?
Yeah.
Can you help me out with this? So what would be delta I sub C if my input is, my small signal input is 1 millivolt?
Would it be 801 millivolts? Or?
What would be 800?
Oh, VBE. Would VBE be 801 millivolts?
In that case, VBE would be 801 millivolts.
Okay.
Okay. But remember, we're looking for a change in I sub C.
Oh, okay.
So what do we do? Now, I see where you're going with this, but don't go there. Because what you could do is to say, well, okay, now I sub C is I sub S exponential of 801 millivolts over 26 millivolts, and I'm going to calculate this, and I'm going to subtract it from this I sub C. Is that where you were going?
Yeah.
Okay, so
kind of.
Yeah, that's a legitimate thing to do, but it's sort of it's not using the small signal simplification. So now you're forcing yourself into a sort of calculating exponentials and stuff like that. Because we're talking about such a small change on the input, all you would have to do is to say the change in I sub C is G sub M times the change in the input. Okay, so all we calculated, the G sub M here is 1 over 3.75 ohm times 1 millivolt. And the change is in 0.267 milliamps. Okay, now think about what we're doing here. So what we said is we are going like this is, say this was 800 millivolts. We're saying, okay, if this changes just a little bit, whatever that little bit is, the millivolt is certainly it's a little bit. 5 millivolts is a little bit. 20 millivolts might be a little too much to do this, but certainly for a millivolt, around this 800 millivolts, if I just have a change of a millivolt, all I have to do is now I can pretend my device is just a resistor and has this, the inverse of its resistance value is this G sub L. And I'm just multiplying it. So like I bet, let's do this. I bet if we did this, it's going to be close. So let's see what would happen. So if we did it when I say the hard way, okay? So say I sub C is, what do we say for the 3 times 10 to the minus 16 amps exponential of 801 millivolts over 26 millivolts. I'm just doing this. If we did not have a small signal model, we would have to do it this way, or if it was not appropriate. Okay, so let's do it. 801, 26. Okay, so this ends up being sorry guys, I gotta do this over again. Okay, so I end up at 7.19 milliamps. Okay, so here we had 6.92. So this is IC2, IC1 was 6.92 milliamps. So the delta I sub C doing it this way is 0.27 milliamps. Okay. So Robert, you see how these are about the same?
Yeah.
But the difference is I have to use, take out my calculator. I mean, I guess, given that I'm no longer good at doing math in my head, I still have to.
Yeah, it's still more work though.
Yeah.
No, yeah, it makes more sense doing it with the GM.
Yeah. So that's how you want to do it. That's like the usage of small signal is you figure out the bias point, and then the small changes gives you, it's easier calculation. Now you always have to think about, hey, is that change small enough that I can do it or not? But 1 millivolt is kind of like, that's and you're always in a bipolar transistor again. You're always comparing that's input to the 26 millivolt value. You're not comparing it to the bias point, none of that stuff. You're always comparing it to the 26 millivolt value. Okay. Okay, so now let's keep going, Robert. So what is the change in I sub B?
So I sub B was beta over GM. No, that's R pi.
Yeah.
No, it was a beta over IC, right?
It's the other way. It's IC over beta.
IC over beta.
Okay. Or it should be delta IC, yeah. Okay.
So it's 0.267 milliamps over 100. So if the way to keep that straight in your head, Robert, is that I sub B is always going to be a lot less than I sub C. Okay, so if you have I sub C over beta, and it's going to have the same, it's going to have units of current. So if you had it be if you had a beta over I sub C, delta I sub C, you would have had 1 over current.
Oh,
right?
yeah.
And so anyway, so this ends up being blah 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 blah, 2.67 microns. Okay. Another way you could have calculated, so this is method one. Another way, which is still a small signal way of calculating it, is we had R sub pi, okay, and V1, in this case, V1 is just across R sub pi. So we could have just said, you know, I delta I sub B is V sub B over R sub pi. So it would be 1 millivolt over calculate R sub 375, which gives us what was it? Same thing, 2.67 microns. So it's just the same method of calculating it. I mean, two different methods of calculating it, both for small signal. You get the same value, whatever you find easier. Okay. Okay, thanks, Robert. And let's go to the next one. Actually, I think I like this because I think we're covering all the ways you could go wrong here. So I think this is good. So example.
Professor?
Yeah.
I'm just wondering. So you mentioned how so IC and IB, are they supposed to be like, are they the same, or like, because I noticed they have the same, you have practically the same millivolts. Is that, oh no, that's micro, is it? Is that micro?
Yeah, this is microamps and this is milliamps. Just because remember that the difference, the ratio is beta. So I sub B is 100 times lower than I sub C. So sorry, it's I'll probably get mixed up over my poor penmanship here. So this was 0.267 milliamps, and these are microamps. So another way I can write this is equal to 267 microamps. It's the same thing, right? So it's basically I sub C is 100 times bigger than I sub B.
And B is given, right?
I'm sorry?
And B is given in the beginning, right?
Beta?
Yeah, beta.
Yeah, beta is given, it's given to you for, it's also given by the manufacturer, or will be given for your midterm or quizzes or whatever. Yeah. It's a device characteristic.
Okay, got it.
Okay, cool. Where are we? Okay, so now, so we did all this stuff. Cool, that's great, but you know, this wasn't like a particularly useful device, right? So we want to use, let's say we put a resistor here to turn this into an amp. Okay, so exactly the same example, except we're gonna turn it into an amplifier. So we're gonna take the same guy, Q1, with the grounded emitter. We're gonna have our microphone. We're gonna have our 800 millivolts. But now we're gonna put a resistor on the collector and call that R sub C. And that's gonna be 100 ohms. So that basically this value here, this V out, is going to be basically a gain version of V1 or V in. So, but otherwise all the other values being the same. Okay. And let's see, what is it asking us? So the first thing is, and you always have to do this. This is like the #1 reason circuits actually don't work well in the lab, or don't work the way you expect in the lab or at work or whatever, So first thing you want to do is verify that Q1 is still in forward active. Okay, so once you guys take a crack at that, we'll see if we can solve it together.
Professor, are we given IC?
I sub C. Yeah, you can just use, because look at, okay, Kevin, good question. So VBE didn't change from the previous example. So this is all, by the way, sorry, this is all from the same values as the previous example, whatever that is. I sub S, I sub 3 times 10 to the minus 16 amps. Theta is equal to 100. So since VBE didn't change, I sub C isn't going to change from the previous example. So you can just use the previous examples I sub C. Now for V1, yeah. Okay, guys, let's see if we can ask one of you guys to help me out here. Kay, can you help me out?
I'm still not sure exactly how to do these, so.
Okay, perfect. I mean, we can do it together. Don't worry. We're all, it's like you guys are all like groping in the dark. It's all right. So, okay, so what do you think we should do? Any ideas?
Well, you kind of gave us a hint that IC is still the same, so.
Okay, so we can write IC going through here is, what was it? 6.92 milliamps. Oops. 6.92 milliamps. Okay. So remember, do you remember what the definition of forward active was for a bipolar transistor?
No, I'm sorry. I don't remember it.
Okay, no problem. That's why we have lectures. Okay, so the definition of forward active mode is there's two conditions. One of them is, so this is the base, this is the emitter. Okay, so the first condition is that the base emitter junction has to be forward biased. Okay. In this case, so this is the way you can tell if a junction is forward biased or not is you want so this is, remember, this is the P side, this is N, this is the N side. If we think of it as PN junctions, okay? So you want this voltage across this PN junction to be positive and, you know, be around, you know, like, so 600, 800, 900 millivolts. So this one is like a check because if you, I mean, it's correct, because if you look at, if I call the base emitter junction as the base, the voltage at the base minus the voltage at the emitter. What I have hooked up here, I have 800 millivolts at the base and the emitter is at ground. So I have 800 millivolts minus 0. So VBE is 800 millivolts. So condition 1 is met. It's the base emitter is forward bias. Okay.
Okay, so Professor, like what we're saying is just that the base to emitter must be positive. And since we do know that the V1 is 800 millivolts, that makes it for sure positive.
Right. Now, not V1, but this other voltage.
This other voltage. Okay. Okay.
Exactly. Though, because you're, as a designer, you stuck this voltage here and you made sure it was.
Okay.
Base emitter was positive. Okay. So you met condition 1. Okay. And then there's a condition 2 that the collector base voltage junction has to be a reverse bias. I.e. that the collector voltage has to be larger than the base voltage. That's kind of the condition for reverse bias. Okay. Now we have the base voltage, right? That's 800 millivolts. You put it there. Okay. Now, what's V sub C? Do you know the collector voltage? So that's the voltage here, right there.
Would it just be the 1.8 volts from the VCC?
It would be if I sub C. Remember, you have a.
Right.
Right.
So it would be the V equals IR. So it's just IC over RC.
Well, so now think about it. You got to do a Kirchhoff's voltage law. So the voltage here is 1.8 volts. Then there's a voltage drop across this, and then you get to here. So you got to do, so the voltage V out is 1.8 volts minus I sub C R sub C. Does that make sense? Basically, you have this current gives you a voltage drop across this resistor, and you have to subtract that from this guy before you get to this guy.
Oh, yes, I see it.
Okay. So 1.8 volts, this is 6.92 milliamps times 100 ohms. God help me, what is that? The book says this ends up being 1.108 volts. V out. Okay, so V out, and that's equal to V sub C. So now we have 1.108 volts. And then on the other hand, so this is V sub C, this is V sub B is 800 millivolts. So V sub C is bigger than V sub B. So now we've satisfied condition 2, which is that the collector base junction is reverse biased, and so we've satisfied both conditions, and we are in forward active. So that was it. Okay, thanks.
Okay, thank you, Professor.
Sure. So now one thing to remember, guys. So, and this is why it's important to keep checking this. Now, let's say for whatever reason, instead of using, because you're the designer, right? You could have picked, 820 20 millivolts or 840 millivolts or something like that. So you could have made this higher. That would have made I sub C higher, which means that the voltage drop, this IR, would have been bigger, meaning this is, if as you make VBE bigger, as you make this VBE bigger to get a higher I sub C, you make this collector go lower, and at some point, this guy will not be forward active anymore. So that's what happens in sort of in your search to get a higher and higher gain, or higher and higher I sub C. At some point, at a particular value of VCC, you're going to take this guy out of bias. So whenever you're designing any kind of amp, or especially like in this class, we'll only be like dealing with simple things like this, you have to keep checking your assumption that this isn't forward active. If it goes out of forward active, all these simplifying equations, all this stuff. So basically, as soon as you go out of forward active, we can no longer use these equations. So you're kind of screwed at that point, and you're not going to get a good amp or anything. Maybe you can get something else, but it won't be a good amp. So, and you certainly can't use these equations because these are all assuming that you're in forward active mode. Okay. So let's see, what's the problem B? Okay, so now, whoops. So now, let me just do this for you guys. So now if you wanna, or do you have enough time? Nah, just 30 minutes. Okay, so part B is, whoops. So B is, what do you say? It says determine output signal with V1 is 1 millivolt. Okay, so now we got this guy hooked up as an amplifier. We've made sure that it's in forward active mode, and we're just giving a 1 millivolt wiggle here. Okay, so now we want to see what the output is. Okay, so if you just look at the, if we know delta V on the input, or delta V on the input, okay. Sorry, delta, if we know delta V on the input, so delta I sub C is going to be GM delta V. Okay, so we're looking at 1 over 3.75 ohms. Times 1 millivolt. Okay, we already did this here. So we basically end up with 0.27 milliamps. So delta V out, okay, is just this 0.27 milliamps times R sub C, which is 100 ohms. Okay, everybody with me?
Yeah.
Yeah, so if I want to see what the gain was of this amp, it's change in the output voltage over the change in the input. The change in the input was just our input, right, 1 millivolt. And the change in output was 27 millivolts. So that ends up being 27. It's unitless because it's just gain. Okay, the volts cancel each other out. So now, basically, we've designed an amplifier here that has a gain of 27. We have a 1 millivolt signal here, we get 27 millivolts here. We put 2 millivolts here, we get 54 millivolts here, okay, and so on and so forth, as long as this input isn't big enough that throws our calculations assumptions out of range. So once you have this and your input is small enough then that's all you need to do is you just need to be multiplying whatever you input you have by your gain value, then you got the answer. Okay, so that's kind of that's the steps you kind of go through here. Okay. All right, guys, I'm gonna stop it here. I think I'd mentioned that we were gonna have the quiz on Tuesday, but we didn't quite cover everything I wanted to cover, so I'm gonna move the quiz to Thursday next week, so we can just sort of quickly cover what we need to on Tuesday, and then it should be that much. And then hopefully we'll move into chapter 5, either on Tuesday, sort of second half of the lecture on Tuesday, or Thursday after the quiz. Okay, guys, any questions?
Thank you, Professor.
Okay, thanks, guys. Take care.
Professor.
Thank you.
Thanks. Hey, Louis.
Yeah, Professor. I saw your email late.
Yeah, do you have time right now?
Yeah.
Okay, do you want to just pop on the...
Yeah, sure. I'll do it right now.
Okay, thanks. Yep.